Just to convince you that this is a very, very general identity, this equal to 0, it should hold in every basis. Doesn't really, we are not using that EA mu is the basis that diagonalizes the metric. So this should be true in every basis. For example, what if we apply it to the basis dx mu itself? Dx mu, if you want, is the basis where instead of the field bind, you have the delta. So let's do it. The covariant derivative of the delta should be and is 0, because it is the exterior derivative. Then instead of omega, you have gamma. Instead of A, you have nu. Instead of B, you have whatever you want, but that is delta, minus delta, A is nu, this is rho mu. And that, of course, is 0. So normally this is just the fact that the covariant derivative of the delta tensor has to be 0 because it's an invariant. When you really change the basis, then you just have a relation between the two connections in different bases. Another thing that we can do is to check the condition, torsionless condition, in the basis, again, dx mu. So we would have some t mu equal to del of dx mu. But this we know how to compute because it is a one form with an index. So we can apply the generic definition of covariant derivative, which applies to every k form, remember, with an arbitrary set of indices. So this is equal to d of dx mu, and then there is a plus gamma mu nu dx nu, because there is an upper space-time index, so there is a plus, it's to the right, to the left, and no, that's it. Since this is 0, t torsionless condition means that this object should be 0, but this is a 2 form now. And since it is a 2 form, which is anti-symmetric in rho and nu, the fact that it has to be 0 is equivalent to say that the anti-symmetric part of this object has to be 0. So the Christoffel symbols are symmetric. You can also write TA as del of EA, and that is del of what? EA, you can also write like this. And then, since del is a covariant derivative, you can apply the Leibniz rule. So this is del EA mu dx mu plus EA mu del dx mu. But this we know is identically 0, and so you get this. which again tells you that the torsion is 0 if and only if in one basis it's 0 in the other basis. This is just a change of basis, and we already know that when you do the change of basis, the matrix for the change of basis gets out. So you can say that this is 0 if and only if that is 0. And so on. So this is very useful. Now you know how to change bases in every way you like, how to define and work out covariant derivatives of any type of objects, with or without flat space, space-time indices, a form, a differential form, whatever it is. And so you know also how to move along the manifold when you have intersections of charts, and in those intersections you have different coordinates or different bases for the tangent space, so these forms EA and so on and so forth. And you know what an invariant object is, which is an object that doesn't transform when you make that change. Let's go back once again to the Bianchi identities. A second Bianchi identity again. Bianchi identity was del R equals 0. And restoring indices, that means del RAB equals 0. Let's view this on the Riemann tensor. So let's write RAB as R. This is a two form, so it can be expanded in a basis of two forms. Like this. We could also expand it in the basis dx mu dx nu. And again, we know now how to switch from one to the other. It's always amount to multiply by a field bind to raise the convert indices, and we know that the field bind always commutes with the covariant derivative because it is covariantly constant. So the Bianchi identity can be written like this. 0 is equal to del of R, A, B, C, D, E, C, E, D divided by 2. Now, if the torsion is 0, when you compute the covariant derivative, you apply the Leibniz rule, you have to act on this, and you also have to act there and there. But if the torsion is 0, you do not need to act with the covariant derivative there. So you can just write 0 equal del R A B C D EC ED divided by 2. And again, here now you have a one form, so you can expand it in a basis of one forms. The basis could be dx mu, and then what you get is what you can call the del mu of whatever, but we prefer to use the basis EF, and then what the coefficient we will call del F, the covariant derivative with an index F. Divided by 2. because it will be easy at any moment to convert from one index to the other. We now know how to do it. Now this is a 3 form. And it is 0 if its coefficients are identically 0. Its coefficients are identically 0 if this object is completely, once it is completely symmetrized in the 3 indices, f, c, and d vanishes. So that means that we have this kind of identity. A, B, you have to write it 3 times with 3 indices and perform the cyclic permutations. Let's say C, D, E, C, D, E, C, D, E. That is 0. So this is probably the familiar form that you know about the second Bianchi identity. If you want to switch to the spacetime indices, you can do it, and it doesn't matter because if you multiply by the field by inside or outside the covariant derivative, as we said. Then there are the contracted versions of the Bianchi identities. To the contracted Bianchi identities, you take this identity and you contract indices with the flat space metric, but you have to use the metric compatibility if you want to cross the covariant derivative under the metric compatibility assumption, which I recall is del of the metric in any basis. This basis is this equals 0. So, for example, if we want to work out Bianchi identities for the Ricci tensor, we must recall what the Ricci tensor is. And in case of the Ricci tensor is a contraction between an upper index and a lower index, so it doesn't require the metric compatibility. That is R, B, D. So let's contract this by, let's multiply this by delta AD. We contract here delta AD, let's see what happens. So that is 0 equal delta AD, that is the Ricci tensor BE, so del C RBE plus del E, and then when you contract A with D, since obviously this object is anti-symmetric in the last two indices, you get minus the Ricci tensor with indices B and C. Minus. The last term is del D, which is contracted with A, So you just leave it like that. RA BEC. So this is a contracted version of the Bianchi identity, which gives you something like the divergence of the Riemann tensor, which is a derivative contracted with an index. Instead, if we want to get the second contracted Bianchi identity, we need to use the metric compatibility that is the scalar curvature. So if we contract, we multiply here times delta eta BE, what do we get? Eta BE, let's see. Yes, so we get 0 equal del CR minus, that is something like, now we have to remember what we are talking about here, because if we raise an index on this Ricci tensor, which is a Ricci tensor, and write it like that, we may get confused with the two form which we used so far. So to avoid the confusion, maybe I write Rich, something like that. BE, so let me see, B, C. The Ricci tensor is symmetric, by the way. We saw that already or not. I don't remember if we did it in the differential geometry part. Let me check. Well, that is maybe something we didn't see. Well, it's a consequence of the properties of the Riemann tensor. We didn't see it, but we can see and mention it right now. In a minute. And the last part is plus del A R. So if we contract with B and E, this is again minus the Ricci tensor with indices A and C. So what you get is the following property. These two contributions are equal. You move that to the other side and divide by 2. Okay. Yeah, concerning the symmetry properties, let me recall, yes, there was an exercise actually. It was more on the Riemann tensor, but let's check that. Here. So when you have the Riemann tensor, you have these interesting symmetry properties, which you should have proved by means of this exercise. If you exchange the first two, then you can lower or raise the indices. That means switching from a basis of differential forms or basis of vectors, but doesn't. Here they are all vectors, so all vectors or all differential forms, it means to raise all indices or lower all indices. Then you have anti-symmetry in the first two and in the second two, and you have symmetry when you exchange the first couple with the second couple. So remember that this was the definition of the Ricci tensor, and therefore it is symmetric because the second and fourth vector are contracted, and so if you exchange the first couple with the second couple, it's like exchanging x and y, and the Ricci tensor is unchanged. So it follows from these properties, and you can translate that in the notation we are using now with the flat space indices. And so, yes, contracting these two indices is, apart from a minus sign, like contracting this index and that index. So that's why you have a Ricci tensor here, but with a minus sign. So this maybe it's better to write in more common notation. Where now R mu nu is the Ricci tensor, so don't confuse it with the two form that we introduced. Okay, so now I think that the part of differential geometry is basically over, and we move to gravity, which means we start with the action. What can we do with these quantities, and how to describe gravity and its interaction with every field. So we proceed as follows. First, we consider today and the next time tomorrow matter fields. Scalars and vectors are easy to couple to gravity. Fermions are not. So fermions will deserve a lot of attention. And after scalars, vectors, and fermions, we will consider gravity itself. So the action of gravity. Still, this is all classical. So scalars and vectors are easy. Let's start from scalars. A scalar field is a function on the manifold with real values or complex values. Let's consider real values for simplicity. If it is a function, you know that when you change coordinates in a chart, it changes like that. It doesn't change, one says. Well, before saying it doesn't change, let's just write what it does without claiming too much into it. The covariant derivative, del of a function, zero form with no indices, that's just the exterior derivative. And so you can write that as dx mu d mu phi, and you can write that as dx mu del mu phi. That means that the covariant derivative is the partial derivative. What is action for scalar fields coupled to gravity. So an action is, well, there are infinitely many. Let me write the simplest one, which is the one we will meet many times, and let's explain some things. First I write it, and then I explain what it is. So what is this? What does that? We can also write the integrand as d for x square root of minus g of some thing that we can call Lagrangian density, actually. So first of all, what does this mean? In flat space, which means when the metric tensor is just eta mu nu, the action, there is no curvature, the action is just the usual action with a kinetic term and a mass term. So what we have done, one says, covariantized these two terms, written in a way that makes them invariant under general changes of coordinates, and added a so-called non-minimal term, because it's just possible to do it. Actually, you can add infinitely many terms, but those have higher dimensions. Just to stay in the simplest, in the realm of the simplest terms, this is it. So why that? What is the meaning, and what is the meaning of this integral? The integral on the manifold. Because from the differential point of view, that's what we have to describe. So imagine, as usual, the manifold as like a sphere, for example. That's a topological space that you can cover with charts, in each of which you have homomorphisms, actually diffeomorphisms, because we want smooth manifolds, taking that chart to Rn. So when you write this integral, it means that you have to integrate on the entire manifold, but you cannot use, you see, you have an integrand here that depends on the coordinates. It depends on the specific coordinates you use in your single chart. Actually, its ingredients depend on the coordinates. As a whole, now we will see it doesn't depend on the coordinates, and that's the whole point. So to understand the integral on the manifold, you have to split the manifold into the integral into a sum of contributions, each of which is in a single chart. And in that chart, you can use the coordinates you want. And in the superposition, and no matter how you make the splitting, the result will be the same, because in any superposition of charts, you will have the same result, because the integrand, even if it is written in a way that is apparently not, it's not manifestly invariant under changes of coordinates, it is invariant. This I think you know, but now we recall that. So that is the idea. For example, in the sphere, you have to split the sphere in the way you like, compute, for example, the integral in the upper hemisphere with some coordinates, and necessarily when you go to the southern hemisphere, you have to change coordinates, because otherwise these are singular. But no matter how you split, this way or whatever, you will never find anything different. So that is why it is written as an integral on the manifold. So that's not a very intrinsic expression, in the sense that the integral is not written in an intrinsically, in a manifestly, let's say mathematically invariant way. We are using ingredients that are dependent on the coordinates, but it's not a problem as long as these combinations of objects transform correctly. And actually, let's see what it means. So we know that phi prime x prime is phi of x, and we know that if we want to change coordinates for the metric, we have to use these formula. And we also have that G is the determinant of G mu nu, and we also know that the integral, the measure d for x times the square root of minus G transforms, let's say, as a scalar. We also, that's easy to compute, the covariant derivative of a scalar, which is the simple derivative. Here it is sufficient to compute the Jacobian, and so you have something like that. Then the inverse of G mu nu, yes, if you want, we can also write the transformation for the inverse of G mu nu. Of x, and then all these Jacobians cancel out when you make these contractions between upper and lower indices, and so and by the way, R is a scalar, the scalar curvature is a scalar, and so also L, the entire squared bracket here, is a scalar. So again, you divide your manifold into separate contributions, each one belonging to a specific chart in which you want to use the coordinates you want, and you know that in every intersection you can just easily switch from one frame to the other by putting primes everywhere. That's it. That's why the integral is well defined on the manifold M. It would not be if we hadn't arranged the integrand in a way to make all these Jacobians disappear when you make a change of coordinates. Now, this of course is not the only action you can write. There are infinitely many terms you can add. Can write some examples. For example, you could take the Ricci tensor, contract it like that. Why not? You could take something like this, the kinetic term, and you raise it to any power you want, and so on. So what is the right action of a scalar field? Well, we just do not know. I mean, the physics should determine the right action. We will see what will determine the right action, but for the moment we do not know. So, for the moment, from the point of view, mathematical point of view, we just need an integral that is well defined on the manifold. And possibly in flat space, it should reproduce what we already use for physical purposes. That's already partially a physical ingredient. But we have to stay general, otherwise. Let's see vectors, vector fields. Actually, that is gauge fields. There are other vectors. Later in the course we will see other vectors, gauge fields. In QED first, for example, in QED you know that you need a vector potential A mu that can be actually embedded into a differential form. And we have already defined the field strength so you have F mu nu equal d mu a nu minus d nu a mu. These are the coefficients of a form, so you are sure that they transform in the right way. Notice there is no covariant derivative here, there is a simple derivative. But you are sure that they transform the right way because you know how differential forms transform. So that is the same transformation as the one of the metric. Again, I repeat, now we will see today if we have time or tomorrow if there is any difference between considering this and considering that. Because considering that also apparently is something that transforms correctly. Is there any difference? But for the moment, let's write the action with this one. This is F mu nu. So the action is minus 1 over 4 d4x square root of minus g, and then you have to build a scalar with two forms, with two free strengths, because you know that the action is of QED, or electromagnetic field, is F mu nu, F mu nu. So you have to raise the indices by means of the metric. There is another possibility, actually. We'll see it later. Now, let's answer the question that I raised a minute ago. What about replacing F mu nu with that So let's write the covariant derivative of this object. We know the covariant derivative is the simple derivative. And then we have a lower index, so that is a yes, let me write it like that, so that's easier to connect to what we did before. So that was something like this. Okay? So that is dx mu d mu a nu, and that is dx mu partial mu a nu minus a rho dx mu gamma mu nu rho. So that tells you that d mu a nu is partial mu a nu minus. We have to be careful to use the indices in the right order, because we are not assuming anything about the torsion. And that's the order. So here you have gamma mu nu rho a rho. Then you subtract the other thing, plus gamma nu mu rho a rho. So what you obtain is F mu nu, which is this, and the rest, you see, the rest would disappear. The rest is the anti-symmetric part of the Christoffel symbols. So the two things are equal if the torsion is 0. But they are not equal otherwise. The point is that even when they are not equal, this object is always okay, transforms covariantly, transforms correctly, because this is a tensor, this is a vector, and the difference between Christoffel symbols is a tensor. The antisymmetric part is the torsion, and the torsion is a tensor, and we will check it tomorrow explicitly. So this object is non-zero, but it transforms correctly, even if separately the variation of a Christoffel symbol is a tensor. Christoffel symbol is not a tensor, but the difference, this is like a variation. This is a tensor. So we will continue tomorrow.